19th of May, 1953. Yucca Flat, Nevada Proving Ground. At 04:35 local time, the Harry device detonates from a 300-foot tower. Pre-shot forecasts issued by the Atomic Energy Commission predict negligible off-site exposure, plume dilution over empty desert, background levels beyond the boundary. By mid-morning, mobile survey teams log gamma readings that do not match the predictions. Not at the test perimeter, but hundreds of kilometers east in southern Utah. Film badges confirm it. Ground monitors confirm it. Within days, milk samples from civilian dairies near St. George show contamination the forecasts never considered. The instruments functioned correctly. The meteorological models functioned correctly. The clearance procedures functioned correctly. What failed was the assumption that air dose was the only dose. That assumption would not survive the measurements. From these readings began the story of the forgotten Downwinders and the limits of forecasting what cannot be seen. The system that authorized atomic weapons tests in Nevada began with paperwork. An Atomic Energy Commission safety authorization, signed and stamped hours before detonation, represented the culmination of meteorological analysis, radiological projections, and acceptable risk calculations. The forms detailed wind speed limits, plume trajectory models, and off-site dose thresholds expressed in Roentgens, a unit measuring ionizing radiation exposure in air. Between 1946 and 1953, the AEC conducted dozens of atmospheric tests at the Nevada Proving Ground. Each required Weather Bureau coordination, military logistics support, and contractor operations. The clearance system functioned on a single organizing principle, that airborne external dose was the dominant risk pathway. If wind carried the plume away from populated areas and diluted it sufficiently, exposure would remain within acceptable limits. Monitoring. Infrastructure reflected this priority. Film badges worn by personnel recorded cumulative gamma exposure. Geiger-Müller instruments measured ambient radiation fields. Mobile survey teams equipped with portable detectors traveled prescribed routes after each shot, logging exposure rates at predetermined stations. The network was designed to track what could be inhaled or absorbed externally during plume passage. What it did not systematically track was what could be ingested days or weeks later. Internal AEC safety manuals from the period describe clearance criteria in precise terms: wind speeds at multiple altitudes, stability indices, forecast plume center lines, maximum permissible off-site exposure rates. The documents assume that radioactive material dispersed in air would dilute to background levels before reaching civilian populations in any significant concentration. Secondary exposure routes, deposition onto crops, uptake by livestock, concentration in milk, received minimal analytical attention. An internal memorandum from 1952, declassified decades later, acknowledged this gap explicitly. Ingestion pathways are considered secondary relative to inhalation and external exposure during plume transit. Monitoring resources are allocated accordingly. The system assumed that what could not be inhaled would not be ingested. This assumption rested on limited empirical data. Few measurements existed of radionuclide transfer through food chains in arid environments. The desert, it was believed, offered natural protection through sparse vegetation and low agricultural density. Clearance forecasts calculated acceptable risk using atmospheric dispersion models. These models predicted where the radioactive cloud would travel, how quickly it would dilute, and what exposure levels would result. The calculations were mathematically sound. The meteorological inputs were state-of-the-art. The instruments were calibrated. What the system did not model was thyroid dose from iodine 131 in milk, consumed by children hundreds of kilometers downwind. The gap between forecast and reality would not become apparent until instruments began recording measurements that did not match predictions. When that happened, the system would face a question it had not been designed to answer. What if the dominant exposure pathway was never the one being monitored? 18th of May, 1953. Weather Bureau stations across the western United States released radio sondes, balloon-borne instrument packages that transmitted temperature, pressure, humidity, and wind data as they ascended through the atmosphere. These measurements, plotted on standardized charts, formed the basis for shot clearance decisions. For the Harry device, scheduled for detonation in the early morning hours of the 19th, the forecast appeared favorable. Upper-level winds showed west to northwest flow, carrying any plume away from Las Vegas and populated areas of southern Nevada. Surface winds were light. Atmospheric stability suggested vertical mixing would remain limited, allowing the plume to drift at altitude without significant ground-level deposition nearby. The clearance criteria were met. The shot was authorized. What the forecast could not fully account for was the behavior of a nuclear fireball rising through multiple atmospheric layers. The Harry device, with a yield of 32 kilotons, would inject an enormous mass of superheated air and vaporized material into the troposphere. As this column ascended, it would encounter wind shear, changes in wind direction and speed with altitude that could alter transport patterns in ways not captured by pre-shot meteorological models. At 04:35 on the 19th, the device detonated. The fireball rose rapidly, punching through atmospheric layers documented in the pre-shot soundings. Within minutes, the mushroom cloud reached altitudes where winds differed significantly from surface and mid-level flow. Post-detonation meteorological observations, recorded in Weather Bureau logs and later compiled in AEC after-action summaries, show a divergence. The plume drifted east, northeast, not northwest, as the primary forecast trajectory suggested. Wind patterns aloft shifted after the explosion, responding to the thermal disruption the fireball itself created. By mid-morning, the plume had traveled beyond the predicted deposition zone. Mobile survey teams dispatched to monitor roads and towns in southern Nevada found readings consistent with forecasts. Teams dispatched to areas farther east, outside the primary monitoring arc, found something different. A health physicist's field log from the 20th of May records the first anomaly. Station Echo 7, Highway 91 south of Caliente. Background expected approximately 15 microroentgens per hour. Measured 120 microroentgens per hour. Instrument checked, readings consistent. The forecast had been correct until the explosion changed the atmospheric system at St. George, Utah in 1953, was a small agricultural community of approximately 4,000 residents. Located 240 kilometers east-northeast of Yucca Flat, the town served as a regional center for dairy farming. Washington County as a whole supported several thousand head of dairy cattle, with milk distributed locally and to surrounding settlements. The area appeared in no AEC risk assessments as a zone requiring special radiological monitoring. Predicted fallout deposition maps, generated using pre-shot meteorological forecasts, showed the highest activity concentrated in unpopulated desert regions north and northwest of the test site. Southern Utah fell well outside these zones. Local milk consumption patterns, documented in public health surveys from the period, followed typical rural norms. Per capita consumption was high, especially among children. Fresh milk from local dairies entered households within hours of collection. No pasteurization requirements existed for milk sold directly from farm to consumer. The supply chain, cow to container to child, operated with minimal delay. This supply chain represented an exposure pathway the clearance system had not systematically modeled. Dairy cattle grazing on open pasture consume large quantities of vegetation. If that vegetation is contaminated with freshly deposited radioactive iodine, the iodine concentrates in the animal's thyroid gland and is secreted in milk. Humans consuming the milk receive internal thyroid dose as the iodine is absorbed and retained. For children, whose smaller thyroid glands and higher metabolic rates result in greater iodine uptake per unit intake, the dose is proportionally higher, and iodine 131, with a half-life of approximately 8 days, remains radiologically significant in the food chain for weeks after deposition. None of this appeared in pre-shot safety. Forecasts. The deposition maps excluded populated Utah counties. The monitoring plans did not include milk sampling. The dose calculations assumed external gamma exposure during plume passage would be the limiting factor. The exposure pathway already existed. Cattle, pasture, milk, children. It simply wasn't being measured. 19th to 21st of May, 1953. Mobile survey teams deployed across southern Nevada and Utah carried portable radiation detection instruments, typically Geiger-Müller counters or ionization chamber survey meters. Their mission: document exposure rates at fixed monitoring stations and along prescribed routes, confirming that off-site readings matched forecast predictions. In Nevada, close to the test boundary, readings aligned with expectations, elevated but declining exposure rates consistent with plume passage and dispersion. By the afternoon of the 19th, most near-field stations showed levels approaching pre-shot background. In southern Utah, the pattern differed. A health physics technician assigned to a survey team recorded measurements in a field notebook, now preserved in declassified AEC archives. The entries, written in pencil with location coordinates and timestamps, document a systematic eastward progression of sampling points. At each station, the technician noted instrument readings, local weather conditions, and any visible signs of deposition: dust on vehicles, discoloration on surfaces. Station designations, exposure rates in millirem per hour, and timestamps appear in neat columns. Station Delta 3, 19 May, 1400 hours. Gamma, 0.15 MRH, background nominal. Station Delta 6, 19 May, 1600 hours. Gamma, 1.2 MRH, above nominal, investigating source. Station Delta 9, 20 May, 0800 hours. Gamma, 3.8 MRH, consistent elevated field. Film badge deployed. Converted to modern units, these readings represent approximately 1 to 38 microsieverts per hour, modest elevations above natural background, but persistent and geographically coherent. The pattern suggested not localized contamination, but broad area deposition from an atmospheric source. Further sampling confirmed the trend. Soil samples collected at multiple sites showed elevated beta activity. Vegetation samples, sagebrush, grasses, showed surface contamination consistent with recent fallout. Swipe tests of vehicle surfaces, building exteriors, and fence posts all returned positive results. The instruments agreed. Independent measurements from different teams, using different equipment, converged on the same conclusion. Fallout deposition had occurred well outside the forecast zone, and exposure rates exceeded background expectations by factors of 10 to 100 at localized hotspots. Background level expectations met elevated field measurements. The discrepancy was documented, systematic, and growing. Late May through June 1953. Milk sampling began as an extension of routine monitoring, not as a response to immediate concern. Initial samples came from dairies in southern Nevada within the nominal fallout zone. When those samples showed detectable iodine-131, the sampling arc expanded eastward into Utah. Laboratory analysis of milk samples collected from Washington County dairies between late May and mid-June documented iodine-131 concentrations ranging from 50 to several hundred picocuries per liter. Converted to modern units, this represents approximately 2 to 15 becquerels per liter, small absolute numbers, but significant when integrated over daily milk consumption by children. The biokinetics of iodine-131 in the human body determine dose. When iodine is ingested, a substantial fraction is absorbed through the gastrointestinal tract and transported via bloodstream to the thyroid gland. The thyroid, which regulates metabolism by producing iodine-containing hormones, concentrates iodine regardless of isotope. Radioactive iodine-131, once lodged in thyroid tissue, delivers continuous beta and gamma radiation dose until it decays or is biologically eliminated. For adults, thyroid dose from iodine intake is limited by gland size and metabolic rate. For children, especially infants and toddlers, the dose is amplified. Smaller thyroid glands receive the same absolute activity as larger ones, but distribute it over less mass, resulting in higher dose per gram of tissue. Higher metabolic rates increase iodine uptake efficiency. Greater milk consumption per unit body weight increases intake. AEC health physicists, working from measured milk concentrations and standard consumption assumptions, estimated thyroid doses for children in affected areas. Internal reports, declassified in later decades, showed dose estimates ranging from tens to hundreds of millisieverts equivalent committed thyroid dose, values substantially higher than External gamma dose from plume passage. One memorandum dated June 1953 summarizes the findings. Ingestion pathway via fresh milk represents the dominant exposure route for juvenile populations in fallout-affected areas. External gamma dose during plume transit is secondary. The external dose appeared modest. The internal thyroid dose did not, and the monitoring system had not been designed to capture the difference. 1953 to 1954. Within the Atomic Energy Commission, awareness of elevated ingestion doses emerged quickly. Internal correspondence between the Division of Biology and Medicine, the Division of Military Application, and Test Site Management reveals a documented recognition gap between technical findings and public communication. A memorandum dated July 1953, addressed to the AEC General Manager from the Director of Biology and Medicine, states, "Recent milk sampling results indicate thyroid doses to children in certain off-site areas may exceed previous estimates by factors of 3 to 10. Dominant pathway is fresh milk consumption following pasture contamination. Recommend expanded food chain monitoring for future operations." Another memorandum, dated August 1953, discusses public information strategy. While internal dose estimates have been revised upward based on milk data, public statements should emphasize that all off-site exposures remain within established safety margins. Detailed dose breakdowns by pathway are not recommended for general release at this time. The language reveals a tension. Internal analyses acknowledge that ingestion doses, particularly thyroid doses to children, represented the highest exposure component. Public statements emphasize that total exposures remained acceptable and that safety protocols had functioned as designed. Both statements were, in their own context, factually supportable. Total exposures did remain below acute. Health effect thresholds. Safety protocols did function according to their written criteria. What had changed was the recognition that the dominant dose pathway had not been systematically included in pre-shot forecasts or real-time monitoring. One internal AEC review, compiled in 1954 and later declassified, summarizes the discrepancy. Clearance procedures assessed atmospheric dispersion and external exposure. Food chain pathways were assumed secondary. Empirical data from upshot knothole indicate this assumption was not conservative for all exposure scenarios. The numbers were known internally. The dominant pathway was identified internally. The forecast failure was documented internally. What remained unresolved was whether and how to communicate these findings to affected populations. The discrepancy was documented before it was discussed publicly. 1954 to 1962. In response to internal recognition of elevated thyroid doses, federal health agencies initiated medical follow-up studies in affected areas. The U.S. Public Health Service, in coordination with the AEC, conducted thyroid examinations and dose reconstructions for residents of southern Utah and Nevada. Survey forms documented residents' history, milk consumption patterns, and other dietary factors that might affect iodine-131 intake. Medical personnel examined thyroid glands for abnormalities, nodules, enlargement, functional changes. Dose estimates were calculated retrospectively based on reported consumption rates and reconstructed milk contamination levels. The studies faced significant limitations. Milk sampling had not been comprehensive during the critical exposure window. Many residents could not recall precise consumption details months or years after the fact. Individual thyroid uptake rates varied. Uncertainty ranges in dose estimates spanned factors of 3 to 5. One Public Health Service report from 1958 summarizes findings. Thyroid examinations of juvenile cohorts from Washington County show no statistically significant increase in abnormalities relative to control populations. Dose estimates for most individuals fall below 50 rad thyroid, approximately 500 millisieverts equivalent. Continued monitoring recommended. The language is cautious. No definitive causation established. Doses acknowledged but framed within uncertainty bounds. Recommendations for continued observation rather than immediate intervention. Another report from 1962 notes, latency periods for thyroid neoplasms following radiation exposure may exceed 10 years. Current findings should not be interpreted as evidence of absence of risk. long-term surveillance essential. The medical tracking documented what could be measured and acknowledged what could not. Exposure had occurred, the measurements confirmed it. Health effects, if present, might not manifest for years or decades. Causation, even if effects appeared later, might remain statistically unresolvable given population sizes and background disease rates. Uncertainty delayed conclusions, but it did not halt the accumulation of data. 1954 to 1958. Operational procedures at the Nevada test site changed in response to findings from upshot knothole. The changes appeared not in press releases or public announcements, but in internal operations manuals, monitoring plans, and shot clearance criteria. Revised AEC guidance, issued in 1954, expanded the monitoring arc to include areas previously considered outside the fallout zone. Mandatory milk sampling was instituted for dairies within 300 kilometers of ground zero, beginning several days before each test and continuing for weeks afterward. Meteorological clearance criteria became more restrictive, requiring greater confidence in plume trajectory predictions before authorization. Shots were delayed more frequently, pre-shot. Weather forecasts that previously would have met clearance criteria were now deemed insufficient. The acceptable off-site dose threshold, while not formally reduced, was applied more conservatively when food chain pathways were considered. One operations memorandum from 1955 states, "All future test authorizations shall include assessment of ingestion pathways via milk, produce, and water supplies. Forecasts shall address not only plume transit dose, but also residual contamination potential in agricultural areas." These changes occurred without formal acknowledgement of forecast failure. No public statement declared that previous clearance procedures had been inadequate. No press release announced that dominant exposure pathways had been overlooked. The system simply adapted, protocols tightened, monitoring expanded, criteria evolved. An internal AEC review from 1957, summarizing 5 years of post-upshot knothole operations, notes implementation of far expanded food chain monitoring has resulted in improved dose assessment capabilities and enhanced protective measures for off-site populations. No test since 1954 has resulted in ingestion doses comparable to those observed in southern Utah during upshot knothole. Technical procedures evolve faster than public messaging. The system learned quietly. 1980s. Decades after upshot knothole, the Department of Energy initiated comprehensive dose reconstruction studies for populations exposed to Nevada test site fallout. These studies, mandated by congressional directive and conducted by national laboratories, employed archived milk sample data, meteorological records, population census information, and modern radiological assessment techniques. The reconstruction process involved multiple steps. Archived milk contamination data, often recorded in obsolete units and scattered across multiple document collections, were digitized and standardized. Plume. Transport models, far more sophisticated than those available in the 1950s, were rerun using historical meteorological inputs. Biokinetic models incorporating decades of subsequent research on iodine metabolism and thyroid dose conversion were applied. The results differed substantially from contemporary estimates. One Department of Energy report, published in 1984, summarizes findings for Washington County. Median thyroid dose to children under 5 years of age, consuming fresh milk from local dairies during late May to early June 1953. Approximately 160 millisieverts equivalent, 16 rad. 95th percentile, approximately 600 millisieverts equivalent, 60 rad. These estimates exceed contemporary AEC calculations by factors of 3 to 8. The discrepancy arose from multiple sources. Contemporary AEC dose estimates had used conservative milk consumption assumptions, often lower than actual reported, consumption in rural dairy farming communities. Early biokinetic models had employed adult thyroid masses and uptake fractions, inappropriately applied to pediatric populations. Uncertainty in milk sampling, sparse spatial coverage, limited temporal resolution had been interpreted optimistically. Retrospective analysis with complete data sets and refined models produced higher numbers, not because exposure had increased, but because the analytical tools had improved. The past, when recalculated, yielded larger doses. One sentence from a 1985 summary report captures the implication: if contemporary dose assessment methods had been available in 1953, clearance decisions might have been different. 1980s to 1990s. The full magnitude of forecast failure became quantifiable when dose estimates from 3 different periods were placed side by side. Predicted doses, calculated before shots using atmospheric dispersion models and assuming external exposure dominated, could be compared directly to contemporary post-shot estimates and to retrospective reconstructions employing decades of improved understanding. A comparative table compiled by a Department of Energy contractor in 1987 illustrates the progression. Predicted pre-shot external dose, May 1953, less than 1 millisievert equivalent. Contemporary post-shot external dose estimate, June 1953, approximately 3 to 5 millisieverts equivalent. Retrospective total dose estimate, external plus internal, 1984, approximately 50 to 200 millisieverts equivalent for exposed children. The numbers reveal a cascading recognition. Initial forecasts underestimated external dose by factors of 3 to 5. But external dose, even when corrected, represented only a fraction of total exposure, when internal thyroid dose from iodine-131 ingestion was included. The forecast system had not simply miscalculated, it had optimized against the wrong endpoint. Atmospheric clearance ensured minimal external exposure during plume passage. It did not ensure minimal total exposure when residual contamination entered the food chain days later. One DOE analysis from 1989 frames the failure explicitly. Pre-shot forecasts assessed atmospheric dilution, not agricultural contamination. Monitoring networks measured air dose, not food chain dose. Clearance criteria protected against inhalation and external exposure, not ingestion. The system functioned correctly within its design constraints. The design constraints were incomplete. The system worked as designed. The design was wrong. Forecasts that excluded pathways did not prevent exposure. They only failed to predict it. October 1990. The Radiation Exposure Compensation Act became law, establishing a federal program to compensate individuals who develop specific cancers after exposure to fallout from Nevada test site atmospheric testing. The Act represented legal recognition of harm, acknowledgement that exposure had occurred, and that consequences, while statistically complex, warranted governmental response. Eligibility criteria were defined geographically and medically. Individuals who lived in designated downwind counties, including Washington County, Utah, during specified test periods and subsequently developed eligible cancers could file claims. Thyroid cancer, leukemia, and certain other malignancies qualified. Applicants had to demonstrate residence and medical diagnosis, but did not need to prove causation definitively. Compensation amounts were standardized: $50,000 per eligible claim for downwinders, $100,000 for uranium miners and millers who faced occupational exposures. The amounts were not calculated as direct compensation for individual dose or harm, but as acknowledgement payments representing governmental responsibility. By 2020, the program had processed over 35,000 claims from downwinders, approving approximately 60%. Total compensation exceeded $2 billion. The approval rate reflected both the stringency of medical and residential documentation requirements and the inherent uncertainty in linking individual cancers to historical exposures decades earlier. No formal apology accompanied the Act, no admission of negligence or wrongdoing. The legislative language emphasized compassion and recognition rather than liability. One passage reads, "The Congress recognizes that certain individuals have been exposed to radiation from atmospheric nuclear testing and may have developed serious illnesses as a result. This Act provides a mechanism for partial restitution." Recognition arrived through arithmetic and statute, not through apology. Numbers became policy. Exposure, once contested, became compensable. 1990s to present, the immediate radiological consequences of upshot knothole. Harry faded within weeks. Iodine-131, with its 8-day half-life, became undetectable within months. But institutional consequences persisted far longer. Radiological assessment procedures changed fundamentally. Ingestion pathways, once considered secondary, became central to pre-shot forecasting and post-shot monitoring. Environmental sampling expanded to include milk, produce, water, and soil. Dose calculations routinely incorporated internal exposure routes. The analytical framework that governed U.S. atmospheric testing from 1954 onward reflected lessons from southern Utah. Clearance criteria tightened. Monitoring networks expanded geographically. Food chain sampling became mandatory. Shot delays became more frequent when meteorological conditions introduced uncertainty about food chain contamination potential. Atmospheric testing at Nevada ended entirely in 1962. Underground testing continued until 1992, but the exposure pathway that defined the upshot knothole experience, fresh milk from pasture-fed cattle delivering concentrated iodine-131 to children, never again received comparable scrutiny under operational conditions. It didn't need to. The mechanism was understood. The monitoring was in place. The forecasts included it. Long-term environmental monitoring in former downwind areas documented the gradual return to background radiation levels. Iodine-131 vanished by late 1953. Longer-lived isotopes, cesium-137, strontium-90, persisted in soil at detectable but environmentally insignificant concentrations for decades. One Department of Energy environmental report from 2005 summarizes findings. Residual contamination from 1950s atmospheric testing remains detectable in selected soil samples from Washington County, but presents no current health risk. Background radiation levels are comparable to naturally occurring variation. The land recovered, the procedures changed, the institutional memory remained. Atmospheric testing ended. The analytical framework it forced into existence did not. What the records ultimately show is not malice or negligence, but structural incompleteness. The forecasting system that authorized upshot knothole, Harry functioned according to its design. Meteorological models predicted plume transport. Dosimetric calculations estimated external exposure. Clearance criteria assessed acceptable risk. The instruments worked. The procedures were followed. The authorization was justified by the standards of the time. What the system did not do, could not do with the tools and understanding then available, was forecast dose from exposure pathways it did not measure. A declassified AEC internal review, compiled in 1956 and released to the public in 1994, acknowledges this gap explicitly. Pre-shot safety assessments for atmospheric tests conducted through 1953 focused primarily on external gamma exposure during plume passage. Ingestion pathways, while recognized theoretically, were not systematically incorporated into dose forecasts or monitoring plans. Experience from upshot knothole demonstrates that this approach was not sufficiently conservative for all exposure scenarios. The language is technical, not apologetic. It describes a learning process, not a moral failure. It documents evolution of understanding, not admission of wrongdoing. The lesson, preserved in thousands of pages of archived data, survey logs, dose tables, and policy memoranda, is procedural. Risk models that exclude exposure pathways do not prevent exposure through those pathways. They simply fail to predict it. Instruments that do not measure ingestion dose cannot confirm that ingestion dose is negligible. Forecasts that optimize for atmospheric dispersion do not guarantee protection when contamination persists in the environment. The Harry shot exposed this gap not through catastrophic failure, but through quiet accumulation of measurements that did not match predictions. Milk samples, field surveys, thyroid dose estimates, retrospective reconstructions, each data set, examined across decades, reinforced the same conclusion. Exposure pathways not measured are not pathways avoided. They are pathways invisible until the data reveal them.